Okay, hello. So as I mentioned in the email where I'm sending this link, there will be no class on July 15th. That's a Monday. So what I'm going to do here is go over the end of the notes that I couldn't finish on Thursday. So you can begin the practice problems on the tables for water during the weekend, okay? Then we are going to finish this on Tuesday. So while you watch this video, you should have the notes as well. Okay, so I am attaching my notes, and bear with me because they are sometimes, not meant to be shared. So many times I am speaking to myself. Okay, so in class today, Thursday, July 11th, we started talking about quality, and we said that quality, X, is the mass of saturated vapor divided by the total mass of a system if we have a saturated mixture, okay? So it does not apply for compressed liquid and for superheated vapor. So if you determine that you have a compressed liquid, quality is an A, all right? It does not apply. Same for a superheated vapor. Now, if we have a mixture, saturated mixture, we have quality, X equal to 0, when we have a saturated liquid, and you can follow the notes, and X equal to 1 when we have saturated vapor. If X is in between 0 and 1, we have a mixture, okay? So X will help us to fix the state in that region where pressure and temperature depend on each other, okay? So the examples we went over in class, we said temperature 100 degrees, quality equals to 0.5. It means that half of the mass of the mixture is saturated vapor. So I ask you guys, what is the pressure? And I don't know if we finished that, but the pressure is 101.42 kilopascals. Okay, so I'm not sure if I finished that. Oh, I think that in class I changed it to 60 degrees Celsius because we're so used to 100 kilopascals, okay? The pressure is much lower then, all right? It will be 20 or something like that kilopascals, okay? Now the next example that you see on the notes, we have pressure 4 bar and saturated vapor. And we want to figure out how much is specific internal energy. Okay, so 4 bar is 400 kilopascals. X equal to 1 indicates that we have a saturated vapor. That means that U is whatever UG is from table A5. Right, so just make sure that you know how to do that. Okay. Now, somebody asked in class, one of the guys who sits in the front, very smart, like, what are we using the quality for? Because, I could have known that the pressure was this value without knowing if quality was 0 or 1 or 0.5 or 0.2 or anything else. So now we see the next part. It says X equal to mg divided by total mass, and we want an expression for V, for a specific volume. So I write over there, V. It is not equal to Vf plus Vg when I'm talking about specific volume because it's an intensive property. So if I tell you that the temperature of half of this, all right, sorry, let me just drop this. The temperature of this is 25 degrees Celsius. I cannot say that this half is 12.5, that half is at 12.5 degrees Celsius. It's an intensive properties. We cannot add it like that, all right? But we can add volume, which is the next line. We see that volume, all right, of my entire system is volume of my saturated liquid plus the volume of saturated vapor on top, okay? Now we know that volume is mass multiplied by a specific volume. So that's what you see right next to that. MF, VF plus mg, VG, or this V that I'm saying right now is specific volume, okay? So now I know that the total mass times the overall specific volume is equal to MF, VF plus mg, VG. I can divide it all by total mass and I get an expression for specific volume of my mixture, all right? And you see there that it's a function of VF, function of VG, and a function of the quality, okay? So we will get the exact same equation for U, and you will see that on the next page. So I want you guys to have that equation as well. U in specific terms is UF plus X multiplied by UG minus UF. Okay, when we have a mixture, that means that when X is equal to 0, that V turns into VF. When it's equal to 1, that V turns into VG. Okay, next page is some examples on quality. The very first example, and I want to say if you have questions, pause and send me an email, text, whatever. I'll be there on Monday also if you have questions. The very first example is 100 degrees. Quality point 25. Find the pressure and find the specific internal energy. The pressure is the saturation pressure. It doesn't matter if quality is 0, 0.25, 0.75, 0.99, 0.1. Pressure will be saturation pressure, okay? Then U will be UF plus X, UG minus UF. We find that value of UF and UG at 100 degrees Celsius, so at A4. And we find that U will be in between UF and UG. So go to your table and make sure that that is true when you calculate it. It will be some number between UF and UG. You are in the saturation region, or the other, I don't know what's going on here, but you're in the saturation region from F to G, okay? Very next example says pressure 300 kilopascals and specific volume 0.5 cubic meters per kilogram. We want to find the specific internal energy. So in this case, the first thing that we're supposed to do is go to table A5, so practice that if you have the time. And V is in between VF and VG, which means that we have a mixture. We have a saturated mixture, which means that for U, we will use that equation, UF plus X, UG minus UF. How do we find that value of X? We know that V is in between VF and VG, so X will be in between 0 and 1, but how do we find it? Well, what we will do is take that equation of V, VF plus X, VG minus VF, and we will solve for X. That means that we get X equal to V minus VF divided by VG minus VF. And just in case you haven't noticed, I am following a set of notes that is also attached to this email, all right? So here we calculate X, and we get that as 0.825. And as I've mentioned before, numbers maybe don't make much sense to us at this point, but they will, because they will eventually. When we discuss topics in 2 weeks or so, we'll see that we want to, for example, maximize this value at the exit of a turbine, because we want the least amount of liquid. As X approaches 0, we have more liquid. As X approaches 1, we have more vapor, okay? Then with X, we can calculate U. And because these examples are very short and straightforward, I recommend that you pause, right? And that you practice this. Are you getting the same, okay? Then the very next one that you see there, that's one of the conceptual ones I do on the board. It says that, let's pretend, all right, that we have an initial state of saturated vapor. That's what that means, okay? Then we have a constant volume process where the pressure decreases. And it asks, what do we have, okay? We can start thinking about it. We're like, we have a saturated vapor and the pressure is decreasing. So we could expect to have a superheated vapor at the end because the pressure is decreasing. However, if that happens, the pressure is decreasing and it turns into a superheated vapor, the volume would want to increase. But we are fixing the volume. We are fixing it such that it remains constant. Therefore, it is not intuitive anymore, okay? I want to take a short pause here to talk about latent energy, right? Because somebody asked about that in class. It was an excellent question. What happens, when we are in this region, like what you're seeing there, and we are keeping the pressure or temperature constant, what is happening to all that energy? So on this email, I'm also posting a link that talks about that. How is that energy being used, right, to break bonds instead of increasing the temperature? Okay, so in this case, we see that if we show it on a TV diagram, that's what we have there, you would have a saturated mixture. So these notes, since you have them, what I recommend is maybe printing them out and writing down the things that I'm saying, or whatever you're practicing, and putting it with your notes, okay? Or maybe rewriting them even, because this is not a very long video, okay? All right, so the very next page, not this one, is a linear interpolation before we see our last example. Now, let's see. Yes, linear interpolation. Okay, the example I have here is from other tables, so I'm going to redo it and I'm going to send it to you, right, the actual numbers. But the example that I'm going to use, so it's this top part here, okay? For linear interpolation, we say that we have a linear relationship between two properties, okay? And we use the fact that, again, that we have a linear relationship and we can find the slope using known values to find another value that we don't know but that we need, okay? So an example of this is if we have pressure 130 kilopascals and we want to find VF. That's the example I have here. If we go to our table A5, we have 125 and we have 150, but we don't have 130, okay? So if we look at VF, we have 0.001048 units, and for 150, we have 0.001053, the units of specific volume. So what we have to do, right, is use a linear relationship between the values that we know, find the slope, and then with that, we find our value of VF, the value that we don't know. And I will send you that solved, all right? So that will be, I don't know the number here because I don't have it solved, but I'll solve it for you so you can pause and you can take a look at it. Now here I have a comment on sig figs because some people have asked me, you know, how many, do I have to be really careful? For example, here, where we have 0.001048, 0.001053. You cannot approximate and say 0.00105. You have to use, you know, more digits than that because the number is so small, all right? Now, again, I am redoing this and sending it to you solved, all right? But this is something that we will use a lot. So we said that from 1 to 2, compressed liquid to saturated liquid, and from 4 to 5, superheated vapor, saturated vapor to superheated vapor. We will assume a linear relationship between P and V. We'll assume the linear relationship between T and V, and we'll do the same for P and U and T and U. We'll assume that because we have values with really small intervals in our tables that allow us to do that. It does not mean that we have straight lines, okay? So just to summarize, so far we've talked about quality, which will help us to calculate properties when we have a saturated mixture. We saw some simple examples, and then we saw linear interpolation that is very commonly used because we often don't have those numbers that are on the tables. So the very last thing that I'm sending you is an example that is much longer than what we've seen so far. On the example, you have it again. And it says that we have a closed system. It contains water and it undergoes a cycle. I will do this in class when we come back. However, I am sending this to you so you can take a look at what's happening here. So you can begin those recommended problems that will post a solution to that on Tuesday, okay? So here we have process 1 to 2, constant volume. We have some of the properties at 1 and 2. We have process 2 to 3, constant pressure. We have properties at 3. 3 to 4, constant volume. 4 to 1, constant temperature. Now, here we're going to put everything together because we know that for constant volume, there's no boundary work. We know that for constant pressure, work is P delta V. We know that for constant temperature, if we are in the saturated region, pressure will be constant. We know that for a cycle, that this is a cycle, initial and final states are the same. So now we want to bring everything together, all right? So here is asking for